Today we have exam 8, chapter 16 due. And since there's no one here in the class with me, I'm going to go ahead and introduce chapter 18. Redox reactions and electrochemistry. And this is the last topic to be covered for this course. And we'll have, let's see. We'll have a review next Tuesday. Today's Thursday. Next Tuesday, and then the following Thursday will be the exam on this material. Then the following week, May 6th and May 8th, I've set aside for review for the final exam. And the final exam will be due on the 13th of May. All right. So we've done gases, acids, and bases. Now we're ready for redox reactions. We got to define what a redox reaction is. There are topics. Okay, an oxidation reduction reaction, which we abbreviate redox. Don't ask me why, except for maybe aesthetics. Redox sounds better than ox-red. In any one of these type of reactions, you have a transfer of electrons. At least one electron is transferred, but it could be more. In our example here, we have sodium metal and chlorine gas, in which an electron is transferred from each one of these sodiums to one of these chlorines, and we produce this table salt. Okay. So in this case, only one electron was transferred. And by that, I mean complete removal of an electron from this element to that element. Now, terminology. When we say an electron was transferred from here, actually, since there are two chlorines and two sodiums, there are actually two electrons total transferred in this process. But what has happened to the sodium is it is oxidized because it's loss of an electron means oxidation. Whereas the electron that was transferred to chlorine, we call that reduced. And it gained an electron for each chlorine. Now, how do you remember this? Well, there's a mnemonic device. Oil rig. Oxidation is loss. Reduction is gain. And it should be here on this page also. All right. And reduction is gain. Okay. Now let's look at this reaction. Where we have SN2 plus 10 2 plus, and iron, 3 plus. And the equation's already balanced for us, so we're not gonna deal with that right now. We will in a few minutes. Notice that there are only cations in this reaction. The reaction environment itself must have negative ions in there to balance these. So what we've done is we've left out those anions, right? There might be a chloride here, it could be a chloride there or a nitrate, we don't know. But for our purposes, it doesn't matter because they are just spectators. They're not involved in the reaction itself. We're only interested in the players, those reactants and products that actually undergo a transfer of electrons. Now, what happens here? How do you go from a 2 plus to a 4 plus? Right? You can't add protons, right? If you add protons, you've changed the element. So you have to think of this in terms of electron movement and balance. If 10 loses electrons, it becomes more positive because we're removing negatives and the protons are left behind unbalanced. So that means this one lost electrons. And what I like to do is draw a tie line between here and here. What happened? Well, in this case, how do you get from a 2 plus to a 4 plus? You have a loss of 2 electrons for each 10. That gets you to a 4 plus. One cardinal rule of oxidation reduction reaction is if there's an oxidation, there has to be a reduction. They always occur in pairs. When you transfer an electron, you may oxidize one, but you have to reduce the other. Right? So in this case, we gain an electron for each iron because it went from a 3 plus to a 2 plus. But notice that there are 2 of them. So if we multiply times 2, we have 2 electrons here and 2 electrons here. That's another rule. The number of electrons lost must equal the number of electrons gained. Okay, so to answer the question, in this reaction, 10(2) was oxidized. And iron was reduced. All right. Okay. Now, we're going to introduce another concept, and this is a bookkeeping scheme for tracking the movement of electrons. The reason we need this is that you don't always have ions involved in an oxidation reduction reaction, right? So ionic compounds can be involved in redox reactions, but you can also have covalent compounds involved in redox reactions. The problem with covalent compounds is you don't have any ions. So you can't do a simple assessment of charge. So we need this bookkeeping scheme so we can track the electrons. And it's called oxidation states. And we assign oxidation states to atoms based upon these rules. Okay, first rule. Any atom in the reaction that is elemental. So it could be a metal like silver or iron, like that. Its oxidation state is 0. And we put a 0 there to designate that it doesn't have a charge either. But if you have diatomic element like that, each one of those hydrogens is oxidation state 0. Second rule is ions. Any ion like iron 3+, that charge is the oxidation state. Or if we have, let's say, chloride, its oxidation state is -1. Now, when you have covalent compounds and oxygen is involved, such as water, right? There are no charges in that molecule. This is a covalent compound. We assign an oxidation state for this oxygen at -2. All right? The only exception to that rule is when you have a peroxide of some kind. So, for example, hydrogen peroxide. Now that oxidation state is -1. Any peroxide, the oxygen in any peroxide bond is -1. Now, the reason that we're assigning these oxidation states, beginning with oxygen, and then we'll include some others, is that some of the oxidation states in compounds can vary, and vary quite a bit, and they have to be calculated. So if you have a molecule with oxygen in it and some other element that we don't know the oxidation state, you have to assume something for oxygen in order to calculate the other one. Hydrogen in covalent compounds is a +1, like that, okay? Except if hydrogen is bound to a metal in an ionic compound, such as our example there is aluminum hydride. Okay? This is a -1. All right. And we know from naming compounds that we've assigned values for ionic metallic elements. Right? The first column, the alkaline metals are always +1. Alkaline earths are always +2. The aluminum, gallium, and indium are always +3. So this one has to be +3. That makes this one -1. We had no choice. Fluorine in any compound is -1. So for instance, HF, right? We know that this one is assigned a +1. This one is a -1. And fluorine is always given a -1 oxidation state. Now, other elements in the halogens can vary. And it depends on the situation as to whether we assign a -1 to any other halogens. Sometimes we have to, and I'll show you some examples of that in just a few minutes. The other rule is for a neutral compound, ionic compound, covalent compound, neutral compounds, the oxidation states must add up to 0. So here we have a -2 for that one oxygen. Here we have 2 times a +2, +2 equals 0. Right? Or if we have this compound, where we have a 3 times -1 is a -3, a +3 equals 0. So whether it's covalent or ionic, the oxidation states must add up to 0 in neutral compounds. But suppose we have a polyatomic ion, like nitrate. In the case of polyatomics, which are actually covalent ions, the oxidation states have to add up to the charge on the polyatomic ion. So we know that oxygen is -2 times 3 is -6, right? Yeah. We need to reserve 1 minus charge for the compound. So we really only need to balance the charge of -5 with that nitrogen, which is +5. So +5 and -6 equals a -1. All right, we covered this one already. In ionic compounds, alkali metals are always +1. So we're talking about lithium, sodium, potassium, rubidium, cesium. And alkaline earths, their next door neighbors, are always +2. Beryllium, magnesium, calcium, strontium, barium. They're always +2. Now we left out their neighbors. If you keep moving to the right, you find boron, aluminum, gallium, indium. Well, aluminum, gallium, and indium are always +3. For some reason, that rule didn't make it into to this set. Okay. When you have chlorine or nitrogen are present with none of the above rules, we can't go to rule 1 through 8 to determine chlorine oxidation state or nitrogen oxidation state. And this is particularly troublesome in covalent compounds. In that case, then we would assign chlorine a -1, just like fluorine. And nitrogen would be a -3, just like it would be for any ionic compound with nitrogen. So this is just since this is a bookkeeping scheme, we can apply that rule and it works. The other reason that we assign this -1 to chlorine, say when it's in a compound with phosphorus. Okay. Phosphorus is to the left in the periodic table of chlorine, which means it's less electronegative. It's not as strong attractor for electrons. So we assign the -1 charge to chlorine, which now allows us to calculate a +5 for phosphorus. If we didn't do that, then we'd have no way of assessing the oxidation state of either one. All right. So let's calculate oxidation states for the elements in each one of these compounds or polyatomic ions. All right, first one, potassium dichromate. Okay. We go to our rules. And what do the rules say for these elements? There's no rule for chromium. There is a rule for oxygen and for potassium. Potassium is an alkali metal, so it's a +1 oxidation state. That's for each one of the potassium atoms. And similarly, -2 for each one of the oxygen atoms. Now, how much do they contribute to the total? 2 times +1 is +2. 7 times -2 is -14. All right. So what we've obtained here is a -12 oxidation state for everything except chromium. Now, chromium must balance that oxidation state with positives in order to make this whole thing 0. So we've got 2 chromiums which have to supply a +12. That means each chromium has to be a +6. All right. Carbonate. Right. Each one of these oxygens is a -2. -2 times 3 is a -6. But we have to assure that what's left over is a -2. So we really only need to balance a -4 with a +4. That way, when we assess the total, we have a -6 for the oxygens, a +4 for the carbon, and that leaves us with a -2 charge. Okay. There. Manganese dioxide. If this is a -2, then we have a -4 total, and the total must add up to 0. So this manganese must be a +4. Okay. PCl5, we did that one before. We have to assign a -1 for chlorine, otherwise we're stuck. So that's a -5, and this one must be a +5. And sulfur tetrafluoride. Right? We have a rule for this one. Fluorine is always -1. So that's a total of -4 contributed by the fluorines. That this must be balanced here, +4. Okay? That's how we do bookkeeping for oxidation states. All right, here's our old favorite, sodium and chlorine, to make table salt. What are the oxidation states? Well, we know that the elementals must be 0. So sodium is 0, chlorine is 0. And then in the compound, chlorine must be a -1. That makes sodium a +1. In this case, sodium is oxidized. It loses electrons. Chlorine is, let's see, chlorine is reduced. And we're introducing another term here. So let's put that equation back on the board. And that's 0. And we're making 2 sodium chlorides. So in order to, we identify sodium as oxidized and chlorine as reduced. Well, what caused chlorine to be reduced? Sodium caused chlorine to be reduced by transferring an electron to chlorine. So that makes this the reducing agent. In a chemical reaction, any species that is oxidized is automatically something else to be reduced. that means the reduced species is the oxidizing agent. Okay. All right. Now here's a reaction where all the reactants and compounds are covalent. So we have methane and oxygen forms carbon dioxide and water. And if you've ever watched SpaceX launch its Starship rockets, they are using this reaction. Oxygen plus methane yields these compounds plus a lot of energy. That's where they get all the thrust for their, Elon Musk gets thrust for his rockets. Okay, what's the question? Well, if we want to determine the oxidation states, we go for elements are 0, right? And hydrogens must be +1 in a covalent compound. So +4 total, that means this must be +4. And then we go to the other side. We've done this one before. -2 +1. -2 means -4, which means +4. Okay. Now, this is the reason that we've assigned these oxidation states is so that we can track oxidations and reductions in the reaction. All right. So if I draw my tie lines, oh, that's not right. That's -4. If we go from here to this carbon, what has happened? In order to go from a negative to a positive, we know that carbon must have lost electrons. It is oxidized. So there's a loss of how many electrons for each carbon? Well, to go from -4 to 0 is 4 electrons. But to go from 0 to +4 is 4 more electrons. That means a loss of 8 electrons for each carbon, which is a total of 8 electrons lost. So, if carbon was oxidized, what had been reduced? Well, hydrogen didn't change. That means methane is the reducing agent. It causes the reduction of oxygen. So oxygen is going from here to there and to there. It's going 2 different places. Starts off at 0 and it's gained how many electrons? Well, to go from 0 to -2, it gained 2 electrons. And to go from 0 to -2 here, it gained 2 more electrons. So it gained 4 electrons. Well, actually, that's not right. If I'm going to do it this way, it gained 2 electrons per oxygen atom. How many oxygen atoms do we have? Well, 2 times 2 is 4. Equals 8 electrons. So there we have the balance of 8 electrons lost, 8 electrons gained. Okay, this is just a review. Transfers may occur to form ions, but they don't have to. So when something is oxidized, its oxidation state is increased. In other words, it becomes more positive. It might stay negative, but it's more positive than it was before. So if we go from a -4 to a -2, it's becoming more positive. That's an increase in oxidation state. And when it's reduced, we have a decrease in oxidation state, or the number becomes more negative by gaining electrons. All right. So let's see if we can determine which one of these reactions is a redox reaction. All reactions are not redox. So we want to determine which one is redox, because when we can track the movement of electrons, we might be able to use those electrons to do work. All right. So I'm going to erase this so I can use the whole board. So the first one is zinc and hydrochloric acid. So the first one, let's see, let me move it down a little bit. Zinc plus hydrochloric acid, it's aqueous, yields, this is aqueous plus hydrogen gas, correct? Two, okay, balance it, 2 here, and that's it. Okay, so we have a balanced equation. First thing you do, well, there's a rule of thumb that can help you instantly identify a redox reaction. And that's where you see an element on one side of the equation, find it in a compound on the other side, or vice versa. You find an element in a compound on the reactant side, and it's a free element on the product side. Either way, you have a redox reaction. Every time, no exceptions. All right, now we prove it. All right, oxidation state 0, 0. Here we have a +1. That means -1 for chlorine. Here we have a -1 and a +2. Okay, this is definitely a redox reaction. Now, where's the, which was oxidized? We went from zinc to zinc 2+. Increasing number means loss of electrons. Actually, 2 electrons per zinc yields 2 electrons that actually moved total. On this side, and that makes this the is oxidized. This is the reducing agent. Okay. And for this one, what happened to the chlorines? In terms of electron movement, nothing happened to the chlorines, but the hydrogens went from here to here with a decrease in oxidation state. They went from a +1 to a 0. So we had gain 1 electron per hydrogen times 2 equals 2 electrons. So that makes hydrochloric acid reduced, and that's the oxidizing agent. Okay. There's our assessment of oxidation states. That is a redox reaction. All right. Zinc is the reducing agent. Right. And hydrochloric acid is the oxidizing agent. So we'll do the next one, B. I guess I better erase this to make room for the rest of it. Okay, we have the dichromate ion. Okay, in aqueous solution. We have hydroxyl ions in aqueous solution. Let's see, two of those. And that gives us the chromate ion in aqueous solution plus water. Okay. Again, in this case, we only have anions. There must be balancing cations somewhere in this reaction, but they are spectators. It could be a sodium here, but it could be sodium for all of them. We don't know, and it doesn't matter. Not to assess the reaction for its potential redox. Okay, we don't have any elements, so we assign -2 to that oxygen, which means -14, but we need 2 negatives left over, so we're only going to balance these -12. +12 total, that's a +6. This is a -1. Excuse me. This is a +1, and this is a -2. So that together gives you a -1. This side we have 4 times -2, which is a -8. We hold out 2 of them for that negative. That means this is a +6. And this is a -2 and a +1. Okay, what happened? Chromium stayed the same. Oxygen stayed the same. Hydrogen stayed the same. This is not a redox reaction. All right. Finish the animations. Well, there's no box around it. We're saying that this is not a redox reaction. Okay, and the last one. We have 2 copper 1 chloride, it looks like. 2 chloride. And this is aqueous, yielding copper 2 chloride plus copper metal, right? Yep. So that's a 0. Chlorines are -1. That makes this one a +1, and it makes this one a +2. Okay. Rule of thumb, copper in a compound, copper element, we definitely have a redox reaction. But we want to assess it for which one is oxidized, which one's reduced. Notice on this side, we have 2 copper 1 chlorides. One of those coppers goes to this compound, and the other copper goes to that element. So we're going to have one of these coppers go here, and one of these, and the other copper goes here. Okay, what happened to the copper that went this direction? Well, it had an increase in oxidation number, which means it's oxidized, which makes it the reducing agent. The other copper went this direction, and it was a decrease in oxidation state from +1 to 0. So this one was reduced, which makes it the oxidizing agent. Okay. Do all our assessments. Yes, it is. Okay. Copper 1 chloride is a reducing agent. And copper 1 chloride is an oxidizing agent. So It's not like the same molecule does double duty. One of those, notice there are two of them. One of them does the oxidizing part, and the other one does the reducing part. This is called a big word, disproportionation reaction. Disproportionation reaction, where you've got one compound in your reaction going two directions, so to speak. All right. So now what we're going to learn to do is balance redox reactions using the method of half reactions. Now, you've heard me say this before. Nature just does what it does. And what we're studying and working with is ways to rationalize, ways to understand what nature is doing. And one of those techniques is the half reaction. We can do this because we've identified the oxidation step and the reduction step, and those can be separated out into two separate reactions. Now, they're both occurring at the same time in reality, but to work with the calculations, it's easier to separate them out before we recombine them in terms of balancing the equation. So we split the reaction into an oxidation step and a reduction step. Okay, so here's an example. And before we actually learn how to balance them, we're going to take this reaction and split it in two. It's already balanced. We're going to split it in two just to show what we mean by half reactions. So we do an assessment of the oxidation states. All right. And then we identify what is being reduced in terms of reactants and then to the product, and then what is being oxidized, and separate those out into half reactions. The reduction step is the manganate ion going to the manganese 2+ ion, but notice we have oxygens in there. So we've got to account for the oxygens in this reaction. And we do that with water and balance the hydrogens with protons on the other side. So that's the reduction step. We went from manganese +7 to manganese +2. That's definitely reduction. But what have we left out? We left out the electrons. How many electrons actually moved? Well, 5. We have one manganese going from +7 to +2. That means we have to add 5 negatives to a +7 to get to +2. Now the oxidation step is whatever's left over. Iron 2+ goes to iron 3+. And in an oxidation step, the electrons go on the product side because we've removed them. They have been lost by the iron 2+. So now electrons are products. Whereas in the reduction, we gained 5 electrons in the reduction of manganese. That means the electrons must be on the reactant side. Where'd they go? Well, they're in the manganese atom now, in the manganese ion. Okay, notice one other thing. This equation is balanced, so the number of electrons on the reactant side must be equal to the number of electrons on the product side for the other equation. Okay. So now, if we're going to balance using the half reaction method, and the first one we're going to learn is for acidic solutions. And then I'll show you how to do for basic solutions. So for acidic solutions, we identify and write the equations for the oxidation and reduction steps for each half reaction. Then we balance all the elements except hydrogen and oxygen. Why would we do that? Because we're going to balance any oxygens in there with water, and then all the hydrogens with H pluses, protons. So we do everything else but the hydrogen and oxygen first. Then we balance oxygens with water and balance the hydrogens with H plus. That's why this is known as acidic solution half reaction method, because we're adding protons. Then we balance the charge using the electrons. Now, as a practical matter, we can do the electrons first, right? It really doesn't matter. You can do the hydrogen and oxygens first, or you can do the electrons first, whatever suits your fancy. Then we need to recombine the half reactions into the final balanced equation. In order to do that, you may have to multiply one or more of the half reactions by some constant value in order to get the electrons to balance. You've got to have the same number of electrons on one side as the other. So it may be necessary to modify one equation or both to make the electrons balance. Then you can add them back together. And then you want to cancel any identical species on both sides of the equation. It's going to be best if I show you an example. So here we got this equation, dichromate ion. Let's see, I'm going to put it here. Oops. Let's get a new marker. Dichromate ion, which is aqueous, and the sulfite ion, which is not that, but this, yields a chromium 3 plus, chromium 3 plus the sulfate ion. Okay, that's what we're given. The first thing we do is decide what parts of this equation go to oxidation step and which parts go to reduction step. So we're going to have an oxidation step and we're going to have a reduction step. But we've got to decide what the oxidation states are before we can determine which one goes where. Right? So this one is 3 plus. This one is a -2 times 4 is a -8. But we're going to hold two minuses out. So that makes this a +6. Okay. And for this side, we've got -2 times 3 is -6. But we're going to hold two of those out. -4 means +4. Okay. And on this side, we've already done this once before. This is a +6. Okay. Which one is oxidized? Which one increases its oxidation state? +4 to +6. Right? So I'm going to keep the arrow here and put stuff on either side. So this one goes from SO3 2 minus and to SO4 2 minus at +6. Okay, So we've used those two. That means what's left is the reduction. So we went from +6 to +3, which is CR207. That's a 2 minus there. And this is +6. Okay, so we've separated our equations. That's the reduction step. This is the oxidation step. There we go. Now we're going to balance everything except hydrogens and oxygens on the next equation. So we've got one sulfur here and one sulfur there. That one's done. We've got 2 chromiums here. We need 2 chromiums over here. Now that one's done. Now we balance the oxygens. We have 3 oxygens here and 4 there. We need another oxygen on this side. There it is right there. And we need 7 oxygens on this side. Over here. All right. So how about the hydrogens? Well, now we've got 2 hydrogens over here. We need 2 hydrogens on this side. As protons. Oh, we're going to do that one first. All right. So now we have 14 hydrogens there. We need 14 hydrogens on this side. There we go, and there we go. All right, now we do electrons. Okay, we need to get our assessment here. All right, for this one, we went from a +6 to a +3. So how many electrons is that? That's 3 electrons for each chromium. But we have 2 chromiums. Right? 2 chromiums, 3 electrons is 6 electrons were added to this side to make that one a 3+. And on this one, we've got 1 sulfur going from +4, +6. That means we have 2 electrons lost for each sulfur. All right. 6 there. And 2 there. Now, before we can combine the equations, we have to balance the electrons. How do we do that? Well, if we multiply this equation by 3, we'll get 6 electrons. So we put a 3 here, 3 there. That's a 6. That's a 6. And this is a 3. Okay. So now that we've got 6 electrons here and 6 electrons there, we can add the equations. Okay. So let's bring it down and try to keep it in the same order. So we have 1 dichromate. Okay. Then we have a sulfite, right? 3 sulfites. Oops. Sulfite. There we go. Okay. And we have 14 hydrogens and 6 electrons. That's it, everybody? 1, 2, 3, 4, 5. 1, 2, 3, 4. Oops, I missed one. Water. Okay, hold on a second. Let's put water in here. 3 water and 14 hydrogens and 6 electrons. There we go. Now on this side, we've got what? 2 chromiums. Okay. And we've got 3 sulfates. Then we have water, 7 water, and 6 hydrogens and 6 electrons. So that's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, we brought everything down. Now, combined equations. There we go on 2 separate lines. Now we reconcile common items on either side. Right? This is by itself. This is by itself. 3 waters and 7 waters. All of these waters are gone. And this becomes 4. Electrons are gone. Hydrogens, we have 14 hydrogens here and 6 hydrogens there. So 6 from 14 is 8. Okay, so that's our balanced equation. Just checking here to be sure. Yep, that's our balanced equation. All right. All right. All right, another example. When we have cerium, two plus, and cobalt, 2 plus, yielding cerium 3 plus and cobalt metal. Okay. Question is, what's the coefficient in front of the cerium 2 plus here? Well, notice we don't have any hydrogens, we don't have any oxygens to deal with. This one we can do without the half reaction method. And here's how I do that. Just draw your tie lines here and here. That's 0. So this is a loss of 1 electron per cobalt. Cerium, excuse me. Cerium. And this one is a gain of 2 electrons per cobalt. So if we're going to balance this one with 2 electrons, this is only 1 electron. What we need is times 2. So I put a 2 here and a 2 here. And that means the coefficient is 2. right? Do our assessment. There you go. And we balance this equation without the half reaction method. If you don't have any oxygens and hydrogens involved in your reaction, then you can use this tie line method. And it's a lot quicker. Okay. Now let's look at this one. The bromide ion plus the manganate ion yields bromine liquid element plus manganese 2+ ion. Now, are we going to need the half reaction method? Yes, because there's oxygen in manganese. It's on one side, oxygen in manganate, and not on the other side. So let's set this one up. Do the half reaction method. So we're starting with bromine in aqueous solution plus manganate in aqueous solution yields bromine liquid and Mn2+. Yes. Okay. This is 0. That's 2+. That's 1-. This one is -2 times 4 is -8, but we balance -7 because we want to hold one negative out. This is a +7. All right. So oxidation step and reduction step. Bromine went from a -1 to a plus. Increased oxidation number, which means oxidation. So we have bromine -1 yields bromine liquid, that's a 2. Okay. That means the manganate must be reduced. And it is from +7 to +2. Okay. Now, next step. Balance the hydrogen and oxygens. Well, first we balance the non-hydrogen oxygen. Those 1-to-1, 1-to-1. There's no need for a change here. So, and there's no oxygen here. So we're stuck with this one, 4 oxygens. So we're going to say +4 waters. Now we have 8 hydrogens. There we go. That one's balanced so far. Oh, my mistake. That did require balancing. So how many electrons are involved? Well, for this one, we went from a +7 to a 2+, which we had to add 5 negatives, 5 electrons. Oops, wrong side. There we go. There we go. And the next one, in order to go from a -1 to a +1, we would lost 1 electron for each bromine, but there are 2 bromines. So that's 2 electrons. Okay. Now, how do you balance an odd with an even? You cross multiply. You take this 5 times here, and you take this 2 times here. Right? So that makes this 10. It makes this 5, makes this 10. And it makes this one 16, makes this one 2, makes this one 10, 2, and 8. Okay. So now we have balanced electrons here. We can combine the equations. There we go. Now we can add them together. All right, so we have 10 bromide ions. We have 2 manganate ions. And we have 16 hydrogens and no waters. Let's see, 1, 2, 3, 1. Oh, electrons. Well, we don't have to bring the electrons down because they're balanced already. We'll just leave those out. So that's 1, 2, 3, 1, 2, 3. Now we'll bring 5 bromine and 2 manganese 2+ ions and 8 waters. Okay. Now, can we cancel anything on either side? I don't see any way to cancel those. So I think this is our final balanced equation. There. Yep. Okay, this is in acidic solution, and you can tell it's acidic because of these protons. That's what makes the solution acidic. What if, though, this reaction were taking place in basic solution? We know it's basic solution because we measured the pH. We know it's basic, right? This is not an acidic solution. Now we're saying it's basic. Well, the way to correct that, right? Once you balanced it in the acidic method, you can convert it into a basic reaction simply by neutralizing those hydrogen ions with hydroxyl ions. So if we add 16 hydroxyls on both sides, okay, that makes what here? 16 waters. Okay. Well, if we do that, now we can assess a balance between the waters. All of these waters are gone. And now we only have 8 waters left on that side, plus 16 hydroxyls. Now this solution is basic. And remember, just because we have this arrow doesn't mean that this is happening in some part of the reaction vessel and this is happening in some other part. This is all mixed together. All right, so there's our change. And that's the balanced equation. 8 waters on this side, 16 hydroxyls on that side. That's what I call the basic method is the fake acid method. You do the acid first, then you convert it to base. All right. So up to now, we've been talking about redox reactions, oxidation reductions, and how to balance those equations. Now we're going to learn what to do with it. what practical application can you have for redox reactions? All right. First of all, electrochemistry. We know what chemistry is, but this is a study of substances and how they change from one substance to another. Well, in this case, we're studying electrochemistry. And we're taking chemistry one step further and saying that in the study of electrochemistry, we're actually trying to track the relationship between the chemical reaction and any transfer of electrical energy. And there's a good reason for that. If we know how the electrical energy is being moved from one place to another, maybe we can intervene and extract some of that energy for our purposes to do useful work. There are two ways to study electrochemistry. One is the spontaneous way, where we have a reaction set up and we've arranged the reaction in such a way that we can access the movement of electrons. Right? This spontaneous reaction is producing electrons moving from one place to another, and we intervene to use that energy. This is typically known as a battery or a galvanic cell. The other way is to set up the reaction so that we can drive it in the non-spontaneous direction. Right? We know what the spontaneous direction will be, but we want to make it go backwards. So one way is forward spontaneous. The other way that we study is to make the reaction go backwards. So an electrochemical cell or galvanic cell, think battery, takes the two half reactions. For instance, these two half reactions, and couples them in such a way that the electrons are transferred from one vessel to the other, from one half cell to the other, through an external circuit. That way, we can intervene in that circuit and use those movement of electrons to do useful work, such as a flashlight. Right? We have intervened and used those moving electrons to make that LED light up. So in this case, we have two reaction vessels. Now, in this case, we've taken the half reactions and physically separated them. All right. So the one on this side, our reaction takes the manganate ion in aqueous solution, acidic solution, and converts it into the manganese 2+ ion. So we're going from here to here. Right? And we have an electrode here to go to the other vessel. And in this vessel, we're taking iron 2+ and we're converting it into iron 3+ with our electrode here. Okay, so which way are the electrons moving? If we're going to take this one and make it a 3+, it has to lose electrons. So that means the electrons are leaving this system and going that direction. And when they get over here, they're taking this manganese +7 and adding those electrons here to reduce that manganese 7+ to manganese 2+. Okay. So this one is causing the oxidation of that one. And this one is causing the reduction of the other. Okay. Now, there's just one problem with this setup. Anybody that studied electricity knows that electricity does not move. Well, it can move from one place to another, but if it does so, then it may build up a static charge. And in chemistry, we don't build up static charges. We work with circuits. In other words, when an electron moves from one place to the other, it has to complete a circuit. So we've got to find a way to connect this one to this one so that we have a complete circuit. And this is our salt bridge. Otherwise, we build up an imbalance in charge on one side or the other, an electrostatic imbalance. So this way, we can move electrons one way, we can move, anions one way, cations the other way, whatever it takes to balance the charge. All right. This is our circuit. And there are a couple of ways that you can complete the circuit. One is a salt bridge. In other words, we put a bridge in here that has a sort of a porous plug in the end so that we don't get wholesale mixing of this half cell with that half cell. All we want to do is allow movement of ions. And the salt bridge allows us to do that. Or we can have a porous disk. Porous disk. Well, they spell it with a K. Okay. A porous disk allows the same thing. Only usually porous disks are more efficient because they allow electrons to move over a shorter, ions to move over a shorter distance. Whereas this introduces some resistance to the movement. So we get what's called internal resistance for the battery. Either way works, but you're likely to get a higher voltage out of this system, right, when you're measuring voltage up here. When you're measuring voltage, you get a higher voltage generally if you're using the same half reactions. The porous disk should give you a higher voltage. Okay. So here's an example of two half cells. And now we have a let's see. All right. So what side was the side of reduction? This is the side of reduction. And by definition, the point or the side with that accommodates reduction is called the cathode. Okay. And the side of oxidation is called the anode. Okay. So this is the anode, this is the cathode. And that definition works no matter what the setup. Anode refers to oxidation, cathode refers to reduction. Another way to look at it is cathode is the site at which cations move toward. So in order to receive the electrons, the cation, or this one, this 7 plus, must move to that location before it can receive electrons. And in this case, the once electrons have been removed, then the ion moves away from. Away mean anode is away from, cathode is attracting cations. Now, by convention, usually the cathode is written on the right. Right? In this example, the cathode is on the wrong side by convention. So typically what you want is the cathode to be written on this side, anode to be written on that side, and there's a reason for that. And it has to do with the way we write shorthand. We abbreviate this whole mess into a shorthand way, and the shorthand always puts the cathode on the right-hand side. Okay, that was the first process. The electrochemical cell, or the galvanic cell, or a battery. The second process, the non-spontaneous process called electrolysis. So we pump energy in the form of electrons into the circuit, and we would drive the reaction. We would send the electrons back that way. That would be electrolysis. If we force the reaction to go in reverse. Now, how do you do that? Well, the galvanic cell is going to produce a certain voltage, and it wants to go this way. So what we do is insert a battery in here with a higher voltage. And that drives the reaction backwards. Example. This may be foreign to some of you students because you're not old enough to remember. Maybe you can go to an antique car show, and you'll see some cars with chrome-plated bumpers. Those bumpers are plated in chrome by this method. We deposit chrome on the bumper by driving the reaction in reverse and taking chromium ions in solution and reducing them to the point that they plate out as chromium metal on that bumper. So what would the bumper be? If you drive the electrons, and the electrons produce chromium metal from the ion, that means you're at the cathode. You're at the site of reduction. You're reducing chromium ions to chromium metal. That's reduction. That's the cathode. The bumper is the cathode. All right. Since this course is only introductory, we're not going to go into as much detail as I would if you were taking the general chemistry course. You'd learn how to actually calculate many of these reactions and quantify them in some fashion. So for a lead acid battery or lead storage battery, and every car that's not an electric vehicle has lead acid batteries in them. I'm not sure. it's possible that the hybrids don't have lead acid batteries because they have to work off of usually lithium ion technology. But every gasoline or diesel combustion engine, internal combustion engine, will have a lead storage battery under the hood. And this is the chemistry that's used. The anode reaction, remember the site of oxidation, we're going from lead, oops. Let's see if this one's working now. We're going from lead in a sulfuric acid solution, and we're going to lead 2 sulfate, and that produces 2 hydrogens plus 2 electrons, excuse me. There we go. So this one's 0. This one didn't change from here to here, and hydrogen didn't change either. Oh, this is the half reaction. This is the oxidation half reaction. Okay, so this one is 2 plus. So we oxidize lead to lead 2 plus. And the reduction reaction is next. All right, this is the anode. The site of oxidation. The reduction is the cathode, the site of reduction. And this reaction takes lead oxide in sulfuric acid, okay, and adds 2 electrons to get lead 2 sulfate plus water. There we go. So there are your 2 half reactions. And these electrons here are moving. They're moving from here to here. And we intervene in here to extract that energy, to get those electrons. In our previous examples of galvanic cells, we had the half reactions physically separated from one another because their environments were completely different and had a salt bridge or a porous disk connecting them. In this chemistry, notice we have a solution in common, sulfuric acid. And the product is the same, lead 2 sulfate. So we're going from plus 4 here, to plus 2 there, 0 to plus 2 here. That means that 2 things. You can have the 2 plates, the lead plate and the lead oxide plate, in the same solution. There's no need to physically separate them. They can share the sulfuric acid solution. No salt bridge is required. Okay, here's the overall reaction. Combine these 2, you get lead plus lead oxide in sulfuric acid yields lead 2 sulfate plus water. Now, what does that do? This overall reaction consumes sulfuric acid, right? So what does that do to the solution? Well, it reduces, it reduces the acidity of the solution. So at a certain point, there's one possibility is that your concentration of sulfuric acid gets so low that the battery doesn't work anymore. And batteries, lead acid batteries used to have plugs in the top, holes in them. And when service stations were full service, while your tank was filling with gas, the service technician would open your hood and put this device into your battery and suck some of the fluid out and test its specific gravity. The higher the concentration of sulfuric acid, the higher the specific gravity. So they could measure on a calibrated scale if your battery was getting close to being exhausted. And if necessary, they could add sulfuric acid to it. Okay. The other problem that arises with lead acid batteries is this compound right here. This is a solid. And it plates out on both of these electrodes will have lead 2 sulfate. Now that's as the battery is being discharged, you are using the energy. But every engine has an alternator in it, which provides direct current through the circuitry and drives the reaction backwards and takes this sulfate and reconverts it into lead oxide on this side and lead on that side. Okay? So when it does that, your battery is charged and ready to deliver current again. The problem is that the reaction takes place at the surface of the electrode, right? And if there's too much lead 2 sulfate on the surface of that battery, then the solution can't get to it and the reaction cannot go, right? And in that case, we used to say the battery was sulfated out. In other words, it was dead and could not be recharged because those plates were so covered with that lead 2 sulfate that we could not reverse the reaction. Okay. So at that point, you take your battery back to a recycler and they put it through a process that reconstitutes the materials and reuses them for new batteries. All right, no need for a salt bridge. When fully discharged, well, actually, when fully discharged, you may not have all of the lead and all the lead 4 oxide converted to lead sulfate. It might simply be occluded on the surface. But battery technology now is much more efficient than it used to be, and the sulfating out is less of a problem. Now, when you apply current or voltage in the reverse direction to recharge your battery, you're converting, now your battery is an electrolytic cell, right? So when you're using the energy, it's a battery or a galvanic cell. When you're recharging it, it's an electrolytic cell. You're driving the reaction backwards to store energy in the battery once more. Okay. So when we've got this battery set up and we're letting the reaction run spontaneously and we're extracting voltage from it, right? The voltage between these two plates is about 2 volts, right? And everybody knows that automobile engines have 12-volt batteries. So how do you do that? Well, you put them in series. 1, 2, 3, 4, 5, 6. You put them in series and connect them. Right? So we'll have the like this, connect that one here, connect that one here, here, connect that one there, 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 and there. And that completes, and this happens inside your battery. There are 6 cells inside your battery, each one producing 2 volts. If you put them in series, then you get 2 times 6 is 12 volts. So that's why lead acid batteries under your hood, you can see they would have 6 ports, 6 little caps on top of your battery, 1 for each cell. Okay. So when they produce this, what we call electrical potential or voltage, think of it as pressure or a push. What's pushing those electrons from the anode to the cathode? This is electrical potential, the voltage. And there's the 2 volts for each cell in your lead acid batteries. And I already mentioned 6 of them in series gives you 12 volts. Now, there are other types of batteries. They call them dry cell batteries. They're not really dry, but they're not free-flowing liquids. So if you poke a hole in them, it's not going to come spewing out liquid. But they do have to be in solution of some kind. Otherwise, the ions can't move. Okay. This is one example of an anode for a zinc manganese dry cell. The alkaline version, which is typically what we see on the grocer shelf or at Walmart or wherever you buy your batteries, is an alkaline version. So those are the half reactions for your alkaline, your dry cell. And let's see. Yeah, good. We have a picture. Okay. Notice that the anode is zinc. That's the site of oxidation. And the cathode is a carbon rod. The carbon rod is there not to participate in the reaction, but to provide a connection, an electrical connection to the outside. Because the carbon doesn't participate in the reaction itself for the cathodic reaction occurs in the paste. Okay? So we need some way to get those electrons out. Well, actually, the cathode, we actually get the electrons in, right? So the positive cell is the nipple side, and the negative side, yes, the negative side is the flat side. And usually the anode is the zinc casing. The battery is made out of zinc, and then they just coat it with something like some polymer for labeling and for insulation. Right. The graphite rod does not participate in the reduction reaction. It only serves as a conduit for electrons. There are other types. The silver cell, right? The mercury cell, which we don't use anymore because obviously mercury. But these are those little flat batteries that you can see in calculators, hearing aids. Actually, there's a little battery that goes in, a 5-volt battery that goes into every computer motherboard. And it's there so that your your computer doesn't lose its profile. Once you establish the profile in the CMOS memory, then you want to hold it there, and that's what the battery's for. Nickel cadmium is a rechargeable battery. Rechargeable devices used to use nickel cadmium. It's not as efficient. It produces a good voltage, but nickel cadmium has a nasty habit. And I'll show you, I'll write it on the board. Nickel cadmium batteries went out of favor for several reasons. One is energy density, right? You couldn't get a lot of energy out of nickel cadmium because the nickel and the cadmium ions are big, right? They take up a lot of room to produce the same number of electrons. So we went to a smaller ion like lithium, and now we can pack more energy into a smaller volume. But the nickel cadmium batteries have this nasty habit called memory, or let's see, recharge memory. So let's say you discharge your nickel cadmium battery in your device to maybe 50%. So it's got 50% of the energy left over that it had to begin with. Well, when you recharge the thing, it thinks, right? It thinks that this is now your new 0 point. So you charge it up to what you think is 100%, but it's really, the baseline now has moved up to 50%. So you only have half of the capacity you used to have for that battery. So that's why when you have a nickel cadmium battery device, it's best if you use it until it's completely dead. It's discharged completely. That keeps the 0 point at actual 0. Then when you recharge it, you get 100% value back from that battery. Okay, another topic. We talked about batteries, galvanic cells. Sometimes galvanic cells occur where we don't want them to occur, such as in a buried iron pipe. So iron buried in moist soil will undergo reactions that produce rust. In other words, we will take iron, metal, and it will go to, oh, that's a solid. It will go to rust. Well, what's happened? We've gone from 0 to, let's see, +3. From 0 to +3, which means we lost 3, let's see. That would be 6 electrons. 6 electrons to here. So buried in the ground, this is the half reaction. Any other, this is the anode. Any other reaction in the soil that can serve as a cathode and extract electrons from your iron and corrode it to rust. Well, the way around that for this iron pipe is to connect a metal to it that is more reactive, that will undergo oxidation and deliver these electrons here from the magnesium and drive the reaction backwards, retaining the iron in the buried pipe. That's called cathodic protection. That's one way to protect the iron. Other ways, you just exclude the surface of the metal from exposure. right? You put a coating on it like paint, or galvanizing steel buckets, right? We used to have buckets that they just take them after the bucket is made when it's fresh. They dip it in molten zinc, pull it out and let the zinc solidify on the surface. That's called galvanizing. Zinc is more active than iron, so it offers a galvanic protection to the steel underneath. Or you can alloy, right? You can add something to the metal that is more reactive than the metal that it's alloyed with, and it will also protect the metal, like stainless steel. Stainless steel has iron and manganese, I think. Iron, manganese, and sometimes a little bit of nickel and some other elements. There are lots of grades of stainless steel now that have been developed for various purposes, physical properties, chemical properties. But essentially, stainless steel was developed so that initially the manganese, and it was in the neighborhood of 35%. So it's very high manganese alloy. This would corrode almost instantly to manganese oxide and coat the steel with this very thin microscopic layer of manganese oxide and exclude anything from the environment to get at the iron underneath. So what that did was effectively protect the iron. And if you scratch it, the reaction is so fast, as soon as you scratch, it instantly produces manganese oxide to fill that scratch. And then I already mentioned cathodic protection. You know, every water heater has a rod, a cathode, they call it, that goes down into the tank of water as it's heated. And if water comes in from the outside and goes into your tank to be heated, if it's particularly reactive, it could damage your pipes. It could damage any of the exposed metal inside the heater. So they put this aluminum cathode in there that oxidizes. Actually, it becomes the anode and protects the rest of your, it oxidizes, it corrodes itself and removes any corroding elements that are in the water. So if you have a dishwasher, you just moved into a new house and you've got a hot water heater that was just newly installed, and you run it for, say, 3 months, 6 months, and your dishwasher, you notice that the water level is not coming up. It may even give you an error message telling you that it's not filling. First thing you want to do is go in that dishwasher and open up the inlet line and look at, there's a screen in there, a stainless steel screen that screens out particles, right? And what you may find is a deposit of aluminum oxide particles on that screen that have come from the corrosion of the aluminum cathode in your water heater. That happened to me. So all you have to do is take out what's left of your old aluminum rod and put in a new one. And of course, clean the screen before you put it back in there. And usually it only happens once for new piping. Now, it may not be a problem for most houses nowadays because they don't use copper piping anymore for their water. They use polyethylene pipes, which is plastic and it doesn't corrode. I don't like them, but that's the way they're making houses these days. I prefer copper pipes. Okay. So which part is the cathode? The buried pipe is the site of reduction. the chunk of magnesium is actually the anode. Now, you may also see on ocean-going vessels, especially if the vessel is in port, it's moored to the dock, and it's sitting there and it's being unloaded of its cargo. And as it's unloaded, it'll tend to rise in the water, right? Because you're removing mass from the vessel. It rises, and what you may see that comes up from below the waterline is this ring of metal discs all the way around the vessel. Those are usually made of zinc. Zinc is more active than iron. So if the vessel is sitting in salt water and say it doesn't have protection, then eventually, as you get microchips in your paint, you're going to start rusting through on the iron hull, the steel hull of the vessel. But if you have that zinc there, then you can turn off all the power to the ship, and it can sit in salt water, and the zinc will corrode instead of the hull of your ship. Now, typically what they do is, while there's power to the ship, they send a trickle charge of electrons into the zinc, and it also keeps the zinc from corroding. So you stop the zinc from corroding, stop the steel hull from corroding. As long as you've got power running to it, you're running an electrolytic cell. And the zinc is there only to protect your hull while the ship is powered down. All right, there's a definition of electrolysis. It's actually a reaction in reverse. So this is one of my favorite reactions. When you take hydrogen gas and oxygen gas and ignite them, they make water. And that used to be my favorite part of the space shuttle launching. It had 3 main engines, and they were run on oxygen and hydrogen. They would produce water and a huge amount of energy and noise and water vapor, so forth, and help get the space shuttle into space. But if you want to run that reaction in reverse, you can take the water and put an electric current into the water and split the water into hydrogen and oxygen molecules. So I used to have a device at a different school I was teaching, and it had a tube here and a tube here, and it has a stopcock there, right? And it had an electrode here and an electrode here attached to a power source. And let's say this is the negative side. This is where electrons are going. And this is where electrons are coming out, right? And this is water plus some hydrogen ions. The reason for that is water is an insulator. It does not conduct electricity at low voltage. So we need a few hydrogen ions in there to make a complete circuit. So at this side, right, we've got water is going to hydrogen and oxygen, and this is 2 and this is 2. So oxygen is going from -2 to 0. So oxygen is being, of the water is being oxidized. It's at the anode. Where is oxidation occurring? Well, where electrons are being removed. We remove electrons here. So this one will produce oxygen gas. And it's collected up here at the top. And this one will produce hydrogen gas, because hydrogen is going from a +1 to a 0. It's being reduced. So electrons are coming in, and they're producing hydrogen. So we got hydrogen gas up here, oxygen gas up there. That's electrolysis of water. Now, this can happen where you don't want it to happen. If you overcharge a lead-acid batteries, then you can turn that into an electrolytic cell and produce hydrogen gas, right? And that means that your battery now can become explosive. So the way we used to deal with that was on that lead acid battery, you have those 6 caps on the top. Each cap had a hole in it to vent any hydrogen gas produced. Of course, when you do this to water, you're reducing the volume of water. So the volume will get lower and lower and lower. And if that's the case, then you just put distilled water in there and you're ready to go again. But how do we test to see which side is which? Well, if we collect hydrogen in a tube, right, we got hydrogen here. Then if we take a what they call a splint, a glowing splint, right? It's just a piece of wood that's been treated so that it prefers not to be lit, but it still produces a glow, right? And you stick that in here, you're going to get a pop, right? When the hydrogen and oxygen mix and you ignite them, you get a pop. On this side, you've got oxygen. So what happens when you put that glowing splint in here? When you don't get a pop, the splint bursts into flame because it has oxygen available now. Okay, so that's one form of electrolysis. And by the way, if we could access a cheap, abundant supply of energy, and I'm not talking about green energy, right? Solar panels, wind energy, they are not dense enough to be useful. I'm talking about cheap forms of energy like nuclear power. Then you could use that to electrolyze water, produce hydrogen as a fuel, and you could let the oxygen go or keep it, whatever you want to do. Then that hydrogen fuel could be used to power our industries. Of course, there are a lot more hurdles to get over in order to make that work. I'm about out of time. Because hydrogen is difficult to deal with. It's a gas, right? But that's one way to not produce any carbon dioxide. All right, we're done for the day. And what we'll do next time we meet, next Tuesday, we'll do a review on this topic and go into the Brightspace course and look at this EXAM9, and you'll find the PowerPoints, you'll find the review document, you'll find the key to the review document, and you'll find handwritten worked problems for the review document. And I'm going to, next Tuesday, I'm going to do a review on this chapter using that review document. So if you choose, you can zoom in on that day and bring your questions into the conversation. Otherwise, we're done for today.